Hello everyone, and welcome to a quick Unity tutorial about Raycasts. To start things off, we're going to actually discuss the word itself and quickly see the theory behind this tool. As the name implies, raycasting is the process of casting a ray, or in other words, a beam that starts from a given point and goes in a given direction. The point is then usually to check whether this infinite ray hits one or more objects in the scene, and those are called the raycast hits. This tool can be a great way to compute lines of sight, click-based navigation, gunshots, and other concepts that can be abstracted as a half-straight line starting from a source point and aimed in a specific direction. So today, let's have a quick look at how we can implement, tweak, and optimize those raycasts in Unity and C#. In Unity, the basic way to do a raycast and check for a hit is to use the built-in physics.raycast method. The typical code snippet for implementing this is the following. First, we set up our raycast by passing in our stat position and our direction. By default, the ray will have an infinite length, but we can add another parameter at the end to limit the check range. For now, we'll just say that whenever we press the spacebar, we run our check for a ray starting at the scene origin and set along the forward Z-axis. If you want to cache the ray to reuse it in a more optimized way, you can make a ray variable with this position and direction first, and then pass the ray variable to the physics.raycast call directly. Then we need to check if this ray actually hits something. This is straightforward because the physics.raycast function returns a boolean that is true if it hits something and false otherwise. So we can just wrap our call in an if check and we'll be checking if we hit something. At this stage, we just check whether the ray hits any object in the scene. We can, however, be a bit more specific and get a reference to the object that was hit by setting up a raycast hit variable and filling it in our physics.raycast call. Now, inside the body of our if, the hit variable contains a reference to the object that was hit. We can access its various components by using .collider, .transform, or .gameObject. For example, we can easily debug the name of the object we hit like this. If we try to run our game and put various objects on the Z-axis, then press the spacebar, we see that we do differentiate between the different game objects in the scene. Now, another very common use case for raycast is to find a position in the scene world based on the current mouse position when we click. For example, this is how you can select a unit in an RTS game, or how you can move an object to a pinpointed position on a map. And this is actually fairly easy to do, we just have to slightly adapt our previous snippet. First, we need to get the current mouse position. This is given by the input.mousePosition built-in variable, and with that we can compute our ray thanks to another interesting util, the camera.screenPointToRay function. The name of this method is quite self-explanatory. It takes a camera instance and computes a ray that passes through a 2D screen point. So finally, we can replace our spacebar check with another one that is on the left mouse button click, and now if we rerun the game, we see that the raycast hits the object we are pointing at when we click. Sometimes, you may want to only allow checks with some objects, either to let your ray ignore and pass through a few meshes, or to improve the performance of your raycasting and just disregard useless results. Here, the trick is to use Unity's layer masks. If you take a look at the inspector of any object in your scene, you'll notice that in the top right corner there is a drop-down to set its layer. By default, Unity creates a few util layers you can pick from, but you can also add your own by clicking on the Add Layer entry. This will bring you to the Tags and Layers settings window, where you can define your own tag and layer names for this current project. Once you're done adding your new layer, don't forget to go back to the objects you want to assign to this layer and actually set their layer in the drop-down to the new option. Otherwise, you would just have created the layer but not actually used it. And it's also important to note that all layers have specific indices. So here our new layer has index 6, and it goes along with its name, my layer. Now, back in our C# script, we need to reference this layer and give its corresponding layer mask to our physics.raycast function. The difference between a layer and a layer mask is quite subtle. The idea is that to optimize the memory usage and performance, Unity, Raycast and physic checks don't use an actual integer index, like the 6 we had before, but its bit mask version. So to get this equivalent value, you have two solutions. One, you can use the layer.getMask function and give it the unique name of your layer. In my case, it's my layer. Two, you can do a bit shifting of the index to get the binary version. So for example, here with 1/6. Note that of course you can also expose a layer mask variable to get an easy-to-use custom inspector to help you select the layers. The last step is just to add this layer mask as the last parameter in the physics.raycast call, and your raycast will now ignore the objects in front and hit only the ones that are behind on the given layer. Just as a bonus, let's see a final quick example. How to get hits on an infinite abstract plane instead of a real game object. For now, the techniques we discussed only work when there is an actual object in the scene to click or hit with our ray. This is nice for computing a line of sight or a bullet trajectory, but it can be a bit too limiting sometimes. For example, suppose you want to place some tiles by hand on the ground plane to construct a free-form platform. You can add tiles endlessly to expand the plateau, and they are all stuck at the same y height position of 0. So the whole point is that here we don't have a real ground plane to hit, we just need an abstract notion of a flat infinite surface with its normal directed upwards to be able to place our tile on this virtual level. To solve this situation, Unity provides us with the plane object, which models this endless flat 3D surface. To create one, you can use the most common prototype of its constructor, which requires a reference point and a normal. Typically, in our case, we can pass the origin point and the up vector to generate an infinite plane at height y equals 0. Then, rather than calling physics.raycast, we can call the raycast method on our plane object. And for this method, instead of filling in a raycast hit variable, the method fills in a float, which is the distance from the start point of the ray at which the hit occurred, if there was any. So we can easily transform this to the actual hit position by evaluating our ray at this distance. This way we can easily have our ready-to-place phantom platform follow the mouse while sticking to the ground plane. And this plane being completely abstract, it is automatically infinite, which makes our playground endless as intended. So there you are, that's it for today. I hope you enjoyed this quick tutorial and that you learned a few things to using Raycast in Unity C#. If you did, feel free to like the video and subscribe to the channel to not miss the next ones. And of course, if you have other ideas of Unity tricks that you'd like to learn, don't hesitate to leave a comment and I'll see if I can make a tutorial on that topic. As always, thanks a lot for watching, and see you soon to more videos on coding and games.